All right, so welcome back. So today we'll be continue in learning induction, and then we'll learn how to actually, or how actually electric generator works. Okay, so here are some of the topic. We'll first talk about the EMF induced by motions, and then we'll talk about electric generators, and then we'll touch on alternating current, and then take a look at the transformer. So this is not the movie Transformers, but the ones that you use to transform high voltage to low voltage, or the other way around. Okay, so let's jump in here. So last time we talked about magnetic flux, which flux is equal to magnetic field cosine of theta times A. Theta is the angle between the normal direction of the surface and the B field. Okay, so in that case, then magnetic flux is equal to BA cosine of theta. So in case of if you have changing B, you have then induced electricity, EMF in the circuit. Or if you have in changing A, you can also have the same effect. You will actually be able to induce electricity in the coil. So this will be what's happening here in this section. And then the last thing is theta here. If theta is changing, then you actually also have induced electricity in the coil. So which we will talk about later in the electric motor or electric generator. So Um, and last time we kind of focused on the changing B field that caused the electricity. So this time we'll start with changing A. So let's take a look on this figure over here. So if you have two metal rails, and then this bar can actually move freely on the rails, and then there's a resistor here. So in this case, then the bar, the two rail, and this resistor, they kind of consist of coil, which is in rectangular shape. Okay, so this is rectangular coil. Now, if this bar is moving to the right in this case, so then you have area of the coil actually is increasing. Okay, so the amount of area increasing or changing. Delta A will be then L times delta X, where delta X is equal to V times delta T. Okay, so it depends on the velocity. So the rate of this area changing depends on velocity. So if that's the case, then you have changing magnetic flux in this coil. So this coil does not like that change. So then you'll actually have induced EMF or induced current in the coil here. Okay, which will be then opposed to the change here. So if you have this bar going to the right, you have the area increase. So it doesn't like that. So then the induced current in the coil should decrease the flux. So that means if you have originally magnetic field going into the paper, now the magnetic field by the induced current should be pointing out of the paper. Okay, so in that sense, then you can use your right hand rule because you know now the B field is coming out inside the coil. So you curve your four fingers in that direction. Your thumb is pointing then in this way for this current over here. So you know then the current is actually going in the counterclockwise direction. Okay. All right. So the induced EMF in this case is then will be equal to BLV. Okay. We'll take a look at the derivation just in a little bit. Okay. So and the according to Lenz's law, so it will tell you the direction of the induced field and the current. Okay, so that's what we just did here for right hand rule number 2 there. And here's another right hand rule number 1. So that gives you the force. Okay, in this case, if the direction of the velocity, so that's the Stump's direction. So in that way, so then the charges inside or inside this rod, okay, positive charge will actually then be pulled upward, so that it will give you also the direction of the current in this guy in the coil or in this rectangular coil will be going in this way, counterclockwise direction. Okay, so either you can use your right hand rule 1 or your right hand rule 2 to determine the current direction. All right. So let's take a look on this diagram over here. Again, two rails and then a resistor, in this case, a LiPo here. And then this rod is moving to the right. Okay, so the change in area over time t, delta t, then should be just this L, okay, times this width here, V times delta t. Okay, so that will be your change of A, and B field is perpendicular to the surface here of this coil. So the theta is it's actually given be 0, cosine theta is 1. So then the total flux should be just B times A, okay, in the case. So change in flux then will be just due to the change in the area. So B times delta A, and delta A, as we just mentioned, should be V times delta T times L, or you can rearrange the term. So it's BVL delta T. Okay, so V delta L or V delta T times L is delta A. So then delta phi is that. And according to Faraday's law of induction, so then the induced EMF in the coil should be equal to the number of turns. In this case, it will be just one turn. And then delta phi over delta t. So delta phi is this guy, and then delta t is over delta t. So that gives you that this delta t and delta t will cancel out. Okay. So induced EMF in the coil, then it will be just BVL. Okay. And in that case, if you are looking at the in the rod that is moving, so this moving rod then acts like a battery in that sense, that to give you the EMF. Okay, so induced EMF. So inside the rod, you should have the induced electric field that kind of similar to driving the charges around in that sense. Okay, so B, so if you do E or V, this is V, epsilon will be V over D, okay, and that gives you electric field. So this on divided by D, which is L, that's the length of rod. So then electric field inside the rod will be B times V, okay? All right. So the force, the magnetic force then in this rod over here, okay? So you can see that if the rod is moving with the velocity V, so the current is I. So then according to this is a rod is a conductor carrying current inside the magnetic field. So F is ILB, okay, that we learned in the previous chapter. And I here can be calculated. You use the epsilon induced EMF divided by R be the current, okay? So in that case, and then times L times B. So there are two B's here, will be squared, and then there's one V, and then there are two L's, L will be squared, okay, over R. So then the force this rod experience, the magnetic force, will be equal to B squared VL squared over R. And then because of that, then in order for this rod to move to the right at constant speed of V, that means you need to pull the rod, okay, with an external force, which should be equal to this magnetic force, okay, in that case. So, so because you are pulling it with an external force, so that means you are applying a mechanical power on the rod, okay? So the mechanical power that you apply should be equal to the force times the speed, okay, which we learned in physics 1. So the force is B squared VL squared over R in the previous slide times V here. So then you would have B squared V squared L squared over R, okay, over here together. Now compare this to the electrical power that is produced in the circuit, which is consumed by the LiPo, okay? So then the electric power will be equal to I squared times R, okay? Or you can do V squared over R, which is epsilon squared over R, or you can do I times epsilon. Either way, they will give you the same. All these three expressions will give you the same answer at the end, okay? So if we just do I squared times R, I is epsilon over R, and then you square that, okay? So all these three terms will be squared, and then R will be squared in the denominator as well, but times R. So then this R will cancel one R in the denominator. So at the end, you'll get one R in the denominator, but B should be squared, V should be squared, and L be squared on the top, okay? So comparing these two powers, the mechanical power you apply and then the electric power consumed by the light bulb, you can see they're actually the same or they equal to each other. So this tells you that the mechanical power you put in actually it's converting to the electric power, okay? So it's just kind of energy conversion there, okay? And that's a way to generate electricity in that way, simple way. So a circuit there, and then one part of the circuit can be moving. If you have the presence of the external magnetic field, then you generate electricity, okay? All right, so let's take a look on this example here. It says, the figure below shows a zero resistance rod sliding to the right on two zero resistance rails separated by distance of L. So L is given as 0.5, and it says the rail are connected by a 10 ohms resistor. Okay, so L here, and then this guy is the R, and it says the B field is 0.75, and the current produced. So the I produced, that should be epsilon over R. Okay, so then you can actually figure out what's epsilon, right? Because you are given I, you are given R, so you can figure out your epsilon. It's finding the speed, so it's looking for V. Okay. All right, let me move to another app here for the better writing with my stylus pen here. Okay, so you're looking for V. We know that induced EMF, right? Induced EMF is equal to BLV, okay? And we are looking for the V. So that means if we can find epsilon, B and L are given, so then we can look for that, okay? Now epsilon also is equal to the I times R, which are given in the question. So then you'll set up that these two equal to each other, okay? So BLV then actually equals to I times R, and you can rearrange. So then V will be equal to I times R over BL, okay? And we have everything that we needed here. So we can actually solve for the V. So just plug in numbers there, okay? So I is given as 0.175 amps. And then you can do R as 10 ohms divided by B field 0.750 Tesla times L 0.5. Okay, all are given in SI units, so that makes life a little bit easier. So all this together will give you 4.67 also in SI units of meters per second. Okay, so that's the speed you need to maintain for this setup to work. All right, so going back to the slide here. Now let's talk about electric generator, okay? So previously we look at a B. If magnetic field is changing, you can have induced EMF or electricity. And if you have area changing, which then you can also have induced EMF or electricity. That's the previous section. In this section, we'll take about look at this case now. The B field is not changing. So it's a fixed permanent magnet here and there. And there's a B field is not changing, so by these two magnets is not changing. And then the coil has fixed shape, okay? So it might have N turns, but the shape is not changing, so the area is not changing, okay? So in the generator, then you actually have a mechanical input over here. You turn this coil, and then in that sense, now the angle between the normal direction of the coil's plane and the B field is changing. So theta is changing, okay? All right. So in that sense, then if you do that, then there's a flux changing in the coil, then you will have induced EMF, which generate electricity. So you're then converting your mechanical energy into your electric energy. Okay. All right. So mathematical wise, it's because theta is changing. Theta is changing as a function of omega times t. If this is a just the um, uniform circular motion in that sense for this coil, that's to term in that sense, okay? And so for circular motion, you can use a sine or cosine function. In this case, we will just use a cosine function. So then for the flux is equal to BA cosine of omega t, okay? You can also just use a sine function that will be the same at the end. So epsilon n is equal to minus m number of turns delta phi over delta t. Again, this is Faraday's law of induction. And then flux is BA cosine. So B and A are not changing. So if you do changing of cosine over time t, so again, this is like a rise over run will give you slope. If you have a cosine function, the slope will be a sine function. Okay, so that gives you sine, and then omega will come out here. So at the end, you'll get n turns, and then times b times a times omega, and then sine of omega t. In here, omega is the angular frequency. Okay, so it's 2 pi over t, or omega is 2 pi times f. Okay, so frequency is f, which is 1 over t, or t equals to 1 over f, the other way around, either way, but omega is equal to 2 pi times f. So the electricity you generate, or the voltage you generate, is a sine function then, okay? Or a cosine function if you start with a sine function. But here you can see as a sinusoid function, it will have a maximum value. Okay, so the magnitude will be whatever is in front of your sine argument over there. So NAB times omega will be your maximum induced EMF. Okay. Now when we talk about the household voltage specifications, 120 volts in the US, that is actually not the maximum. Okay, that is the average, kind of average, not technical average, but it's called the root mean square of the induced. If we are talking about average, half of time is positive, half of time is negative, average will be zero. So that makes kind of makes also zero sense because then when you calculate for power, you'll end up with just using zero power, right? But we do consume power. So another quantity to use is the root mean square quantity. Okay. So root mean quantity square is defined as the, so if you are looking for root mean quantity, root mean square of the voltage is 1 over square root 2 of maximum of the voltage. Okay, so V maximum or epsilon maximum in this case. All right, let's take a look on this one. It says a rectangular coil, 25 centimeter by 45 centimeter. So now the dimensions are not in SI units. So you wanted to convert them into SI units first. Has M 150 turns. This coil produces a maximum EMF of 75. So maximum EMF is given when it rotates with angular speed. Okay, so angular speed will be the omega, 190 radians per second in a magnetic field of B. Find this magnetic field B. Okay, so let's take a look on this guy. So we can first calculate the area, right? So area will be the width times the height. So A will be 25 times 10 to the minus 2 meters, right? And then times 45 times 10 to the minus 2 meters, okay? And you can calculate that. This 75 is the maximum EMF, and then maximum EMF we know in the previous slide that should be M number of turns times B field times A times the omega, okay? And we also have N, so this guy is N, okay? And then A is this up here, and then omega is given, so this guy is omega here, so then we can calculate basically what's the B field. So B field in this case then will be equal to the epsilon max over N A omega, okay? So maximum is 75 volts divided by number of turns is 150, okay, 150, and then the area will be the 25, or you can do 0.25 by 0.45 maybe, but 25 times 10 to the minus 2, and then also 45 times 10 to the minus 2, okay? And then omega, it's 190. That's in SI units already, so that's great. All right, so then you will get your B field as the 0.0234 in Tesla, in SI units of Tesla. Okay. Okay. So going back to the slide there. Now let's go back to chapter 20. So in the previous slide, or maybe just one more here, so you can see the electricity generated by a coil like that is going to be a sine function or cosine function, right? So that means half of time you get positive voltage, and then the other half of time you get minus voltage. And if you look at the current, half the time you get positive current, half the time you'll get negative current, okay? So such electric signal is called alternating current signal. So which is in chapter 20 that we intentionally skipped it. Okay, so in that case, V voltage is a peak value times the sine function. Okay, and then if you have a resistor, according to Ohm's law, if you have a resistor in the circuit, then the current will be equal to V over R, which is the peak V over R times the sine function. So then you also get a peak in value in the current. So current I is equal to a current peak times sine omega t. Okay. So when the voltage on the element, on the resistor in this case, and then the current, if they peak at the same time and they have zero at the same time, so then this is called the two in phase. So they peak at the same time, they are zero at the same time, they have minimum at the same time as well. Okay. And then if otherwise, they are called out of phase. Okay. So again, if we talk about the average of either voltage or current, because half of time they are positive, the other half they are negative, so then you'll end up with zero for the average, okay? So then that's not very useful when you are describing their behavior, but we'll use root mean square quantities. Root mean square, that means root mean square voltage and root mean square current, okay, here. And the root mean square quantity, it should be you square them and then you do the average of them. So then it's actually equal to half of the maximum squared. Okay, and then you take square root for that. You get 1 over square root 2 of the maximum. Okay, so the root mean square quantity then is equal to the maximum divided by square root of 2, or 1 over square root 2 times maximum. Okay. So this is what happens when you square it. Okay, so then it's all positive, and then average will be halfway. So then it will be you actually have maximum being squared and then divided by 2 for that. Okay, and then take a square root. So we can then calculate the power consumed by the element. We can do I squared times R, which then will be the I peak squared sine square times R, because I is a sine function. Okay, so if you average that, so then you are averaging all these terms together. I square and R, they are constants, they are not changing. Okay, so then you don't have to average those two. But sine square omega t, so that's varying, so you need to do average of that. Now, sine being squared, okay, so then that's that. So it's all positive, but it's ranging just from 0 to 1 in that case. And then if you are doing average, then you'll do just halfway there. So it'll give you 1/2, okay? So 1/2 comes from the average of sine square omega t, okay? In that case. So in that case, you get 1/2 I square peak times R. Now, remember, if you do peak square and then 1/2, that actually gives you the root mean square quantity squared, okay? So then the average becomes I root mean square squared times R, okay? So average in the AC circuit, then it's actually the root mean square quantity I squared times R. And similarly, you can do this through the other two expressions of electric power. If you do V square over R, then it's the V peak sine square over R, and do the average the same, V square peak and over R, that's constant, but you sine just the average, the sine square omega t, that will give you 1/2. Then 1/2 of peak square will be the root mean square of the voltage square over R. Okay, so the same, again, the same. The average in the AC circuit will be V square over R again, but the root mean square of V, okay? And the similar thing you can derive for the calculating P equal to V times I, you'll get to this result. So average power then will be equal to VRMS times IRMS, okay? So again, this is why then in a couple of slides ago, I talked about the specifications in your appliance. Its current and voltage are both referring to the RMS quantities, root mean square quantities, okay? So household appliances are expressed in the RMS values. So the power, the voltage, and the current, okay, they are just all they are all the RMS quantities, okay? Let's look at this example here. So it says, what's the peak current through a 1500-watt room heater that operates on a 120-volt AC power? Okay, so now let's look at this here. So this is the P, the power. So you're given the power, okay? And then you're given this, okay? So there are three expressions. So P could be equal to I by RMS, okay, square R, or V, again, square by RMS quantity over R, or you can do V RMS times I RMS, okay? So this guy given is VRMS, okay, and we are looking for I peak, okay? So looks like we can use this power equal to the third expression here to find IRMS, right? Once we have IRMS, then we can find I peak, right? Because I peak is square root 2 of IRMS, okay? So we can do that. So we can calculate IRMS equals to P given over VRMS, okay? And then I peak is square root 2 of that IRMS. So that means it will do square root 2 times the 500 volts over the 120 V, okay? And that gives you about 5.89 amps, okay, for the peak current value. All right, let's go back. So now let's take a look on electric motor. Okay, so if you have a toy car when you were little, it will have a motor or other kind of motorized toy. That's what's happening there. So what you have there, it's a device looking like this called motor. You actually have electrical as input and the mechanical as output. Okay, so either driving the wheels or um, tires or whatever. So you put that in and then this guy comes out. So and this is the same, exactly the same components as an electric generator, but just the reverse process, okay? For the generator, you have mechanical as input and then electrical as the output, okay? Um, Now for a motor, because of that, now the um this guy here, or maybe a little bit on motor. I feel like I did not explain clearly how the motor works. Okay, so motor works is you have input current over here. So the input current here through the coil, these two sides, then it's a loop of coil in the electric magnetic field. So there's a magnetic force here. So then it will have magnetic force on one side and then also on the other side. So that makes the whole thing turn. Then that generates a mechanical output. Okay, so that's how it is the reverse process of an electric generator. And if you have that coil now that is spinning in the magnetic field, then this then again um, produces this will make the flux through this coil changing because now the angle of the between the B field and the normal direction of the coil is changing. Okay, so then it will it's like a generator again. So in this case, it will produce a EMF in here, which then will be against the input EMF. So this is called back EMF. Okay, so it depends on your input electrical uh, voltage. So if you are using the 120 volts as the input. So then this guy could be the back EMF here could be as big as 112 volts, depending on how the speed of this guy spinning, right? Because the uh, EMF produced is having a maximum value of NBA and omega, so it can depends on omega. Now, if you overspun this guy, then this guy could be greater. Okay, so then the electricity actually is flowing into here, into the input side. Okay, so you're actually now consuming less power in that case. Okay, all right. Um, So the last section we'll be talking about today is on transformers. So again, this is now for the cars turn into robots, that kind of transformer. But you probably have seen some devices nearby the high voltage power lines like this. So those are transformers. Okay. So in the high voltage power lines, um, the household voltage is not the higher one, right? It's pretty much like 120 in the US or 240 in Europe. So in that case, but using high voltage, you can reduce the loss of power through the lines because higher voltage, that means you are actually having less current in the wires, in the lines, and the lines has fixed resistance or fixed resistance that's not changing so much. So then lower current, that means lower I square times R for the power dissipation there. But then when you are closer to the household, okay, so then you want to have a step down. You want to reduce the voltage. Okay, so there's typically a couple of steps, and then on the power poles, you'll typically see a cylinder shape of like cam. That's the another transformer there. Okay, so from high voltage step down to the substations and then to the power line, still relative high, but then just right before the household, it will be stepped down again. Okay. All right. So the way transformers is constructed is using this kind of coils, one side, and then also coil on the other side. So one side, the input side is called the primary coil, and then the output side is the secondary coil. Okay, and then with this ion materials, the ferromagnetic materials that to retain the magnetic flux produced by this coil in the structure here. Okay, so the magnetic flux is the same here, or the magnetic field here and here and here. They are all the same, kind of uniform throughout here. So it depends on how many turns you have on one side and then the other side, okay? Because flux will be according to the Faraday's induction law, voltage in the secondary coil, the induced one should be equal to minus n delta phi over delta t, okay? And in the primary side, it will be minus np delta phi over delta t, similar equation, but depends on, so phi will be the same, will be the b times a will be the same. In that case, if you have cross-sectional areas are the same. If not, then you'll take into account of that, okay? But typically they are the same. So then the ratio of these two voltage, secondary over primary voltage, is then just proportional to the number of turns. So you have more turns on this side, you get higher voltage. If you have less turns on this side, you'll get smaller voltage. Okay, so this equation is this called the transformer equation. And if we have also current included, so the power by the power plant is fixed, and then through different transformer, it should be also hopefully the same on the other side, okay, as well. So power in the primary is the same as in the secondary, okay? So then this is transformer equation, and because V and I are inverse proportional to each other because power is fixed, okay? So then if we are looking at the ratio of the current in the secondary over the current in the primary, then it's the other way around, okay? So you'll flip the two. So then it's NP over NS, okay? All right, so let's take a look on this example here. So this one says the electric motor in the toy train requires a voltage of 4.5 volts. Find the ratio of turns on the primary coil to the secondary coil in the transformer that will step the 120 volts household voltage down to 4.5. Okay, so your laptop's adapter, your phone charger, similar, or toy train charger, whatever, it's actually made of a transformer in that case, okay? So it's looking for a ratio of turns on the primary to the turns in the secondary. So we are looking for m number of turns in the primary over number of turns in the secondary. So that should be equal to the voltage in the primary over the voltage in the secondary, okay? So in that case, so simply the primary is input is 120 volts divided by 4.5 volts in the secondary. Okay, so the output there. So this gives you 26.667. Okay, or you can just say 27. So that's the ratios. Okay, so if you have 27 turns in the primary, then 1 turn in the secondary. So typical is more than that, maybe like 100 on the secondary, 2700 on the primary. Okay. All right. So what we learned today is the if we have part of the circuit that is moving, then this motion will cause the electricity, will generate electricity in there. This is called motional EMF. And we look at the electric generator, how it works. And we talk about the alternating current signals, electricity signals there. And then we also look at the transformers at the end, okay? So we'll stop here today and then we'll come back next time. All right, see you guys.